chronological order, and in particular the lecture of today will be devoted to anyons. So I start by summarizing what we saw about the excitations of the toric code yesterday, which we saw it's a sort of strange pathological case of anyons. And in particular, when we consider all the possible combinations of the excitations on top of the ground state of a toric code, we must essentially include four possibilities. The idea is that you have the toric code, which is defined in some space. You consider some part of this system where you may have or may not have some excitations. You look at it from distant enough in such a way that you cannot distinguish the internal structure of this subset. You just do measurement by moving things around this part, and you want to know what are the possible topological charges that appear here. And the possible topological charges are these four. The identity, which corresponds to the vacuum of having either completely no anyons or perhaps a pair of electric charges that are close enough and you know that they may fuse together into the vacuum. The same is true for the magnetic flux. And finally, I have to include this further charge, which is the product of E and N. So in my subset, I have a single E charge and a single N charge. Seen from far enough, disappear as a new sort of topological charge, a new sort of excitation. So the trick is that I'm no longer able to distinguish the internal structure of this thing. These charges characterize not only the elementary excitation in the system, but also whatever subset of these elementary excitations you want to describe. So, for each one of these charges, for each combination of these charges, we must distinguish what are the fusion rules. And we already saw that essentially for the toric code, the two electric charges may annihilate together to give me the vacuum because they are obtained from some string of the Z kind, and by applying then the same string I go back to the vacuum, or I can apply also different sort of string and go back again to the vacuum, and the same is true for the magnetic fluxes. So in this case, these are called self-conjugate charges because applying them twice brings me only into the vacuum. And then I told you that we must define the field, the charge psi as the product of E and M, and by considering all the possible string operators, we obtain that the product of an E and psi is equal to M, just because you can multiply this by another E and the two E annihilate each other. The same is true, so similar relation you have for the product of psi with magnetic flux, which gives you the electric charge, and finally two psi annihilate, and we will see that psi is actually F. So, about their statistics, we saw that if I consider a pair of E or a pair of M, with respect to the same kind of particle, D and M, the M are essentially bosons because I can exchange their positions just by applying strings of a single kind. Whereas something less trivial happened when I try to move a charge M around a charge E, or I try to exchange their position in the lattice. It cannot be exactly done, but essentially you must consider in this case that a single exchange is consistent with a single particle moving. So two exchanges are a single particle encircling the other. And in this case, since the string operators involved are of different kind, there is an anti-commutation which appears so that we obtain that R square is equal to -1, which means that a single exchange is dictated by the phase which is R. Finally, to understand the braiding of the other charges, we must consider what happened with psi. And essentially, as I told you, psi must be seen as a composite object of Ne and Nm. So once I move, exchange the position of 2 psi, essentially I can decompose this operation in the operations related to the single components of the psi, and you obtain that essentially you have 2 distinct non-trivial exchanges of Ne and Nm, and therefore overall this is a minus sign. So you have twice this phase, and R psi psi is equal to -1 without the square. So it is different from here. And this is more or less the anionic content of the toric code. More in general, we may consider what is called a generic abelian anion, and I will define it better later on. But let us assume that we have a single quasi-particle that I call A, such that R A is equal to some non-trivial phase. That I call this theta A. In this case, this non-trivial commutational relation, well, this non-trivial exchange relation of the anion of the kind A allows me to say that if I have some sort of two-dimensional system with a toric boundary condition where this excitation live, then all the spectrum of this system, or the ground state in particular of this system, must have some degeneracy. And this comes out from the existence of essentially 2 symmetries. So I am assuming that I can reannihilate A somehow. So either I have A and A bar, which goes to the vacuum. So each topological charge has also the anti-charge. And you may see these operators T1 and T2 as the creation of a pair charge-anti-charge, which wind around one of the trivial cycles of the torus, for example the blue one. So they go around this cycle, and then in the end they reannihilate on the other side. So I start from the vacuum, where the energy is 0, for example. I end in the vacuum when the energy is 0, and however I moved this pair excitation from one side to the other in a non-trivial way, because I'm winding somehow the non-trivial cycle of the torus. This may be applied to both the non-trivial loops in the torus. And the interesting thing is that now T1 and T2 do not commute anymore. And to see this, we must consider what I also brought yesterday about D and M in the toric code, which means that essentially I have to consider this operator. So I create and annihilate a pair of A and anti-A particles along one of the cycle. I do the same along the other, and then I do the 2 opposite transformations. If I write this thing in space-time, I can deform this process in a process in which I create the 2 pairs and move them far apart, create another 2 pairs and move them far apart, then I close the first cycle and I close the second cycle. And I can deform this process in this other process, where you see that essentially I am braiding 2 of these particles twice, and I obtain that essentially all this operator is equal to 2 exchanges of A with A. So the conclusion is that if this R square is equal to 1, it means that this is equal to 1, it means that this T2 and T1 to the -1 commute. So I have the degeneracy. Otherwise, if this phase is non-trivial because A is neither a boson nor a fermion, then what happens is that this commutator is not trivial, and I obtain two symmetries of the system which do not repeat themselves, and they give me some degeneracy. This is, for example, what happens for some fractional quantum states like the Laplace states for sodium or something more quantum good. So, more in general, I would like to define what are anyonic models. Let's start to say that anyons must always be localized and get excitations, and they must be indistinguishable with themselves. And furthermore, they live in a two-dimensional system, and when I exchange the position of two of them, I have to represent this process with some non-trivial unitary operator in general. For the case of abelian anyons, this non-trivial unitary operator is just a single phase, so it's a trivial operator, it's one times one operator, and it's not so interesting. But we will see that there are more complicated cases in which I have to include a bigger space, and it's become a non-trivial operator.
Theta A is a real number or?
Yes, it must be real, and it actually must always be rational with respect to pi. So it's a fraction times pi. Yes, because otherwise you have bad stuff happening, localities, and some inconsistency of your theory. I don't know whether some mathematician attacked the problem whether this theta A is completely rational with respect to pi. But for our cases, it will be always functional. So, I was telling you before that essentially we will have an anyonic system living in a two-dimensional space, and I may consider a set of exchanges on the position of two particles, and essentially this defines a sort of braid in space-time, where you have these world lines which braid one around the other, but they are never cut and they never coincide in a certain point. This means that I want anyons to be localized and to be far away enough in such a way that they do not really interact. If I consider that two anyons become too close to each other, usually in a physical problem, you have some interaction that enters and spoil a little bit this picture. So we are always considering a gap system with a well-precise correlation length given by the gap, and we are considering these anyons as being far apart, distant with respect to this correlation length, in such a way that the effect of braiding them is just dictated by their statistics and not by their interaction. Furthermore, since we are neglecting all these sort of excitations and we never put anyons too close to each other, the result of this process is always independent on the particular path that I adopt. Essentially, I may have perturbation, local perturbation in the system, but the statistics and the final unitary operator which maps this state into this state do not depend on the detail of the path, but only on the topology, only on the structure given by this braid. So, this is why we usually say that anyons provide with their statistic representation of the braid group. If these exchanges are the ones of a fermion or a boson, you have that for fermions this gives you a -1, for bosons this is the identity. And in the end, the only important thing to describe the last state in terms of the first one is to consider which exchange happened, without how many actually, but without considering the order, because for fermions or bosons we always have that R is equal to R -1. Whereas for anyons, the two processes are different, because in one case I braid clockwise, and in the other case I braid counterclockwise. Essentially this theta A is different from phi. phi minus theta A. And so I must keep track of the order in which I am exchanging them, both in time and both if I am applying clockwise or counterclockwise exchanges. That's why one can say that for bosons or fermions, the only important thing is the last distribution of these particles and thus only the permutation of these particles in time. Whereas for anyons, you must really keep track of the full braid. That's why they must be described, their statistics must be described by the braid group. So I guess that now I have to define the braid group, and since I come from Munich, essentially I learned that in there are intuitive examples of the braid group, which you must, well, you can particularly appreciate during Oktoberfest, but for the purpose of this lecture, unfortunately, I will have to give you a more mathematical definition of the braid group without boring you too much. However, you have to think that at the beginning we have n anyons, and each anion defines a strand, a word line, and essentially the braid group is the group generated by all the exchanges, either clockwise or counterclockwise, between neighboring strands. So the generators of this group are a finite number, which scales with the number of anions. However, the group is infinite. And in particular, all these braidings must obey the following commutation relation. If the two braidings are far enough, for example this one and that one, it is not important whether you apply the first one and the other, and they must connect. Whereas, if the two braidings are close enough, so they share one strand essentially, you must apply what, so they must fulfill the Young-Baxter equation, this relation. And I guess that speaking about integral systems, someone else already told you about the Young-Baxter equations. However, to give you an idea of what the Young-Baxter equations are, they tell me that this way of representing the word lines and this way of representing the word lines actually correspond to the same process. And if you look at this, essentially I am exchanging the position of the red particle with the blue particle surrounding the green particle in the middle. And I can deform this way of representing this process into that without actually changing the topology of this braid. Not theory, this would be a right master move. I don't want to bother you too much. However, the important thing is that the braid group is defined by these generators, and they must obey the Young-Baxter relation. They are close, otherwise they must connect. So, about abelian anions, they give you the most trivial representation of the braid group, which is an abelian representation, and that's what I was writing before. So the exchange of two anions of the same species is given by a phase, and you may consider this phase as a sort of Aharonov phase. So you can usually describe these abelian anions in terms of composite objects of a charge and a flux, in such a way that this phase is the product of this charge with that flux. This way of reasoning provides us a sort of spin statistic way of looking at their braiding, also for this kind of anions in two dimensions. Essentially, the spin statistics for this topological spin, which is theta A, tells me that when I exchange two of these composite objects, essentially I have to consider that this red charge is going halfway around the blue flux, and this red charge is going halfway around this blue flux. And I can rearrange this picture by telling that there is a red charge which is going all the way around the flux. So essentially this relates what happens when I exchange two anions of the same species, to what happens when I rotate a single anion by 2 pi. This is why it's a sort of spin statistic theorem. And of course, the result is the same. And this is a powerful tool that we can exploit also to understand what happens when we braid two different sort of abelian anions.
Sorry, but before you stipulated that these anions had to be some large distance apart. But when you're forming these kind of bound pairs, they have to be a long distance apart within the pair as well, or not?
So here I am considering this as an elementary anion, and these are two different objects. So this is a charge and this is a flux. So I don't care. This is a mathematical way of thinking about a single anion, and they must be as close as possible somehow. And you have to consider their motion as being rigid. We will see that in a while. It's important, however, that I keep the two particles far away, because, well, for abelian anions this is not a problem, but for non-abelian anions, since there are different, we will say about that afterwards, but I want to avoid interactions that may either change the energies or give me some unwanted phase or do something worse. So, overall, I don't care if this is it's just a mathematical description. And however, this is a powerful mathematical description because I'm telling you that we can consider this system of A and B, which are fused in a third anion of the kind C. So you may imagine this as being a big anion of the kind C, or as being two distinct A and B. If I exchange now A and B, this amount to do the following operations. First, I have to rotate by pi the full system. So I am taking this big anion C, and I just apply a rotation of 2 pi of my plane, moving it around. So you know that the phase that we acquire is e to the I theta c in this case. But this is not really an exchange of A and B, because I end up with A and B on reverse. So I have to rotate back singularly A and B. This is why this phase is theta A and theta B appear. So overall, the single exchange to the factor of 2, sorry, because I was rotating only by pi. The single exchange of these A and B gives me a phase, and this phase can be defined as a function of the three parameters, the three topological spins of these charges. And, well, this is a way of seeing this relation, but I guess that with Giuseppe you started also to look at the fusion rules of conformal field theories, and you see that in conformal field theories, when you do the OPE, usually there appear this term which depends on the conformal weights of the primary fields associated to these anions in this case. So we have that at least for abelian anions, but there are generalizations also for non-abelian ones. These topological spins are related to the conformal weights. Another example of this would be yes.
Theta C is not a function of theta A and theta B, so it's completely independent.
Yes, it's independent. No, you do not have. No, in general it is independent because consider it as independent.
I'm sorry, I don't really understand that A and B, they are different objects. This means that they have a different charge and different amount of
yes.
force. That's okay.
Yes.
Okay.
And so if you exchange them twice, you go back in the initial state up this operator R square. If you exchange them once, since they are distinguishable, you can somehow detect what you did. And for example, you already had some lecture on bosonization, and you may consider this phi A, phi B, and phi C as bosonized fields, so Burrello operators, let us say, of this form. I take B, GI, and A, phi, B, GI, and B, phi, and their product gives me Z1 minus Z2 to the power A and B times the operator A plus MB phi. And you can recast this relation in that one by observing that the conformal weight of these objects are MB squared over 2 and B squared over 2, and this MA plus MB squared over 2. So if you calculate this difference, you obtain So far I talked about abelian ions, where we have only phases, and all these unitary operators are phases. Now we would like to go to higher dimensional representations of the braid group, where these objects are really matrices, not anymore single phases. And to do this, we must somehow enlarge our Hilbert space when we consider the fusion of two different ions. So let us say that we have a pair of ion A and B, and now the pair, the possible states of a system with these two ions must be more than one. So we will have fusion rules that brings A, B, C times C. This is essentially a way of listing all the possible topological charges that a set of these two ions can acquire. And this is a way of introducing some degeneracy, because if so these coefficients in our case are always either 0 or 1, they tell me which fusions are allowed and which do not. And in particular, I'm saying that this pair must assume a state, and this state is taken in an Hilbert space that I can represent as the sum over C of other states of actually Hilbert spaces. So this object leaves the states of this object leave this Hilbert space. And the important thing is that if I promote the R exchanges to matrices, in general, the sigma which correspond to these R, so the braid generators corresponding to the exchange statistics of these objects, do not commute anymore with each other. That's why these objects are called non-abelian ions. And let us go to some more concrete example. This sort of fusion rule, you can imagine it as what happens, for example, when you consider two different spin 1/2, and in the end you obtain that the pair can be either in a singlet state or in a triplet state. For spins, somehow you have some local measurement of what is happening, because you can independently measure this spin and that other spin. This is not true anymore for ions, because we want that local operators not distinguish the final state. However, if you consider the Hilbert space which describes this fusion of two spin 1/2, you have that you start from two states to describe this spin, two states to describe these spins, and you obtain that these 4 states overall are distributed in a singlet and 3 states in a triplet. So essentially, these B, A, B, C correspond to the Hilbert spaces on the right part of this equation. Whereas for ions, we do not really have a description for what happens on the left part, because these are not objects with an internal structure, an internal degree of freedom. However, this is an example of how these fusion rules may appear. And in particular, in this lecture and also in the following, we will deal with two kinds of non-abelian unions. The first family is the one which is called of the Ising unions. I don't know if Giuseppe already spoke about the Ising minimal model. However, this is the fusion rule of the primary fields in the Ising model, if you consider only the one of the sector. And however, these fusion rules, characterize two objects that in physics are slightly different. To say that when I write in this way, I already am speaking about anyons, and these are thought to be the excitations which appear in a fractional functional state as being finite. Someone of you heard about these strange things that happens in quantum world. Whereas in this case, I will consider the same fusion rule, but for different objects that are the Majorana modes appearing in topological superconductors. There are slightly small differences between the two. Essentially, while in the quantum world systems, these objects have an electric charge, which give non-trivial abelian phases, unbound phases. For the Majoranas are neutral. But to the purpose, so this will affect the Brady statistics of the two things, but the non-abelian part of these models is exactly the same. The other model that I'm going to consider is the one of Fibonacci unions, and so far in nature we are very far to realize Fibonacci unions. However, there are two candidate systems that host them. One is again related to fractional quantum model, and is a rate-resized state, something 12/5, and the other instead is again realized by combining superconductors and fractional quantum Lorentz states of different kinds. However, apart from this curiosity, you see that these objects are non-abelian because I end up in two possibilities. So when I take a pair of these objects, this pair can be found in two different states. And so that in general I will represent these fusion rules with this matrix n. So perhaps, let's say that in general to describe a full system of non-abelian unions, I need to introduce some ingredients that specify this model, and these ingredients are exactly these matrices that dictate the fusion rules that are the answer. Then I need to introduce some fusion, some associativity rules of these fusion rules, and we will describe them later. And then, of course, the Brady rules, and so the representation of the Brady group. And all these objects must have some inner consistent structure that allows to calculate them. However, now I would like to focus a little bit better on the matrix n. And essentially, I will use different ways of writing these fusion rules to emphasize different things. So this fusion may be represented by saying that I have two charges, A and B, and the output charge is C. So with this representation, I'm saying that I have an union entering here, or more in general, a topological charge A entering here, a topological charge B entering there, and they fuse together to give me a topological charge C. So C essentially labels the state of these two areas. And as I told you, this state is inside an inverse space that I can call B, A, B, C. In general, for us, since we take time to be either 0 or 1, but never with higher degeneracy, this inverse space is actually composed by a single state. And in general, if I have a pair of elements A and B, this lives in space which is given by the direct sum of all these fusion vector spaces. And as I told you, gives me the dimension of this fusion space. And this is important because I can consider combining more than two topological charges. So I may have AB which go to C, right here, and then I ask for reference when I add charge T, and the final output will be here. So I want to describe the system in which I have three different ions now, which fuses in an overall total charge which is. Do you have questions? No. So essentially, to describe all the possible states, I have to consider this label C. And we see that this state lives essentially in a space which is given by A and B fusing in C, and then C and D fusing in D, sum, direct sum over C, and this is a tensor product. So that I may ask what is the dimension of this space, and the dimension of this space is given by the matrices. It's just the sum over C of n A, B, C, N, C, D, E. So that here I am summing over this index, and this allows you to say that may represent this as a sort of matrix in which first I consider the addition of charge B to the system where I was in A. So consider this as a matrix. This is A and C, and then multiply it for a matrix of this kind, C and finally E. So that you see that this sum is just the product of the two matrices, so that I can interpret this matrix as, roughly speaking, a transfer matrix that allows me to go from the charge A to add the charge B, going to C, and then to add the charge C, going to E. And this allows me to evaluate number of states, for example, in chains of these unions. Furthermore, well, I will introduce these parameters that are called quantum dimension of the unions, and so I will explain in a while what are these quantum dimensions, but they fulfill this relation in such a way that if you consider this n as a matrix, essentially this relation is telling us that n applied to a vector n applied to a vector d is equal to na applied to vector d is equal to dA times the vector d, where d is a vector that has one component for each of the topological charge in my system, and in particular its components are dictated by these values dA, dB, and so on and so forth. So we have that dA is an eigenvalue of NA. So in particular, once I write n ABC, I have that I can say that A is non-abelian if the sum over C of A in A and C is greater than 1. So that I have at least two different resulting topological charges. So I already told you that these matrices N, A, B, C may be considered also as matrices that are a sort of transfer matrix. And this means that when I consider this sort of system, let us take a collection of aliens A. At each step I fuse, so the first step I fuse the first two, and this gives me a a total charge for this pair, which is B1. Then I fuse also the third anion in the system and evaluate the total charge of these three quasi-particles, and the total charge is B2. Then I add A again, and the total charge of the first four particles is B3. So essentially, if I consider this system, I can define one of the states of this system by labeling all the partial total topological charges of the system. Essentially, I take the total topological charge up to a certain point. By varying B1, B2, B3, and so on and so forth, I obtain a basis which allows me to describe all the states of this model, essentially. This is translated in what I was writing you before by iterating it again and again. I say that the overall invert space where I have small n particles of the kind A is given by this direct sum over all these partial charges, the partial total charges of this tensor product. And the matrices N allows me to evaluate the number of states inside this Hilbert space, and especially by applying the relation that I wrote here and iterating it a lot of times, you see that the total dimension is given by the product of all these matrices that in this case are always equal. So essentially I have to take this particular element of this final matrix that is the product of N minus 1 and due to the Perron-Frobenius theorem, we know that for N going to infinite, this case like the highest eigenvalue of the matrix NA. So this is the definition of the quantum dimension of the anion A. It is the highest eigenvalue of its fusion matrix. And well, this is very abstract somehow, but I would like to specify it better with an example, which is the example of Fibonacci anions.
Yes. So what was the topological charge? Was that the eigenvalue of N? Or?
This is not the topological charge, this is the quantum dimension.
What was it that you mentioned topological charge? Was something you call topological charge?
Yes, so I'm telling you that you can take a collection of anions that have a topological charge of the kind A, a charge of the kind A.
Okay.
And to specify which are the states of this chain, you can consider what are the fusion products of all the charges before a certain point. So to specify fully a state in this chain, I must say the first two anions fuse in a charge B1. Then the first three anions fuse in a charge B2, which is also obtained by multiplying B1 with A. Then the first four fuses in topological charge B3, so that by specifying the string of all these charges that describe the system up to a certain point, I identify one of the states of the system. And so I must count what are all the possible states, and the answer is given by these fusion matrices.
Yeah, so I was just confused by the word, so it's just an anion. You could say topological charge.
Yes, sorry.
Yeah.
I am saying you have to consider, this is because essentially a single anion may always be seen as a collection of something bigger that ends up in this topological charge. So you see that you may consider A as being elementary anions, and then however I'm fusing A and A to give B1 and then A to give B2. But if I consider this block, I can start from here saying that the total topological charge of this block is B2, even though I have some inner structure now, because there are different states labeled by B1 that may have the same total topological charge. So the picture that I was labeling before essentially was writing we must consider the fusion of three anions. Here, if A is an abelian anion, in principle I will obtain different results here, represented by B1, and then I use all these possible results with A to obtain B2. So if I look only at this free anion for far enough, what I see is just B2, is the total topological charge. But if I zoom, then I must distinguish different states that are doubled by different values of B1. And are there other questions? So, let us try to understand this structure in the case of Fibonacci anions. The Fibonacci anions have these non-abelian fusion rules that tell me that two Fibonacci anions may either annihilate and give me the vacuum or give me overall the same charge of a single Fibonacci anion. And I can represent this rule by saying that once I have a system that has a total topological charge tau, and I add another tau, then I may end up either in a total topological charge 1 or in a total topological charge tau. This is one of the building blocks of what are called Bernoulli diagrams. And the other fusion rule is that trivial, because of course if I combine a Fibonacci anion with the vacuum, I obtain a Fibonacci anion. So if my system up to a certain point has an overall total charge which is the identity, by adding a Fibonacci anion, I obtain a total charge of a Fibonacci anion. So while here I have two possibilities, because this fusion rule displays the non-abelian character of Fibonacci, here, starting from the identity, I may only jump on the total charge tau. So the matrix tau that you may obtain from this rule, is actually 0, 1, 1, 1. This means that to obtain the identity by adding a tau, I must be in the state which was characterized by tau. Instead, to obtain a tau, I could either be in the identity or be in tau. This somehow describes this transfer matrix, what happens essentially when I add a Fibonacci anion to a system of Fibonacci anions. For this matrix, I can calculate what is the quantum dimension of the Fibonacci anion, and I obtain that this quantum dimension corresponds to the Boolean addition. And so it is not only irrational, but somehow it's the most irrational number of Boolean. And in particular, the important thing is that its square is irrational too. This is a peculiarity in other things. So if you understand this representation of the fusion rules in terms of the matrix, it is simple enough to understand what happens when I have a set of Fibonacci anions. I have that the first two fuses either in the vacuum or in a tau. If the fuse is in the vacuum, when I consider a third Fibonacci anion, overall they must have a tau charge. Instead, if it is the first two fuses in a tau and they add another tau, I may end up either in the vacuum or in the tau. And this is what this Bernoulli diagram is telling us. So I'm starting from a first anion here, which has a total charge tau. I add the second anion, and I may end up either in a system with a total charge tau or in a system with a total charge which corresponds to the vacuum. Then, if I am here adding the third one, I can either stay on top or go on the vacuum. If instead I am in the vacuum, I am obliged to go on top. The number of possible states, once I add a set of non-abelian anions, is given by the number of possible paths to arrive to a given total charge. So this product of the n matrices is just counting all the number of paths that allow me to arrive at a certain point. And if you see the number of paths that allow to arrive at a given total topological charge tau after the addition of n Fibonacci unions is given by a Fibonacci number. That's why they are called Fibonacci unions. And if you go in the thermodynamic limit, you know that the Fibonacci number scales as the golden ratio to the power n. And so we find out that this quantum dimension is essentially telling us how fast the number of states increases when I start to add these non-abelian unions. If you consider simply spin 1/2, of course, this dimension will be 2, because for each spin 1/2 you have 2 states, and so you multiply by 2 the full system that you had before. But in the case of non-abelian unions, essentially, you cannot simply multiply the number of states that you have up to a certain point with the degree of freedom of the new non-abelian unions, because you must take into account what is the total topological charge to a certain point. So, as I was mentioning you, however, the n matrices are only the first element to specify an anionic model. And importantly, as Giuseppe was saying yesterday afternoon, these matrices must obey a sort of associativity. And this associativity tells me that if I have the collection of free ions, so I consider free ions A, B, and C, and I impose that their overall total charge is equal to B. So that I'm specifying the total charge without caring about the inner structure of this system. I have two possible bases of representing this system with the free and exclusive meaning, which are either the construction in which I choose first A and B to obtain some X, and then X and C to obtain E, or the other possibility is the same system but different bases. I just choose to use before B and C, and they gave me Y, and then to fuse Y and A, and they finally must give me E because I wanted this to be the same system. So essentially, here X is labeling the inner degree of freedom of this system, the possible states that the system assumes in a basis. And here Y instead represents a different basis, a different choice of this basis. However, the overall degeneracy of the system, the number of independent states, must be the same here and there, and that's why we recover this relation. If I fuse first A and B into X, and then X with C into D, I must obtain the same degeneracy of doing this other path in the diffusion rate. That's why, essentially, all these states live in the same Hilbert space, and I may represent this Hilbert space into different classic bases, essentially. So, there must exist a unitary operator, a basis transformation, which maps the first, the basis, so the X basis and the Y basis, so that each state, now I write it as a cat, classified by X, must be written in terms of sum of some matrix xy of this state in Y. And in particular, this matrix, however, must depend on the overall Hilbert space, and this F matrix, therefore, must depend on A, B, and C, which fuses in E, and has indices that are X and Y. So there is a change of basis from this description to this description and vice versa. So F is always unitary. And this is very important because when you want to describe the gradings of these objects, or when you want to describe interaction between these objects, usually you have recipes to understand what happens for nearest neighbor aliens, but you must be able to write it properly in whatever basis you want. So the F matrices are the tool that you use to write down the physical operations that you do in your system. And so this is what I explained to you. There is an interesting connection with conformal field theory, which was emphasized also by Giuseppe yesterday, and that is essentially that you may see this as a conformal block of the fusion of these two fields, whereas this represents the fusion of these two fields. But overall, the correlation function must be the same. Or you may see this as a sort of transformation from the S channel and the C channel in a scattering process. Also in this case, the things must correspond. In group theory, these F matrices are also called 6J symbols because they have these 6 indices, even though ENIOS cannot be really described by groups, but you need some extension of group theory. So, the final element define a fully characterized linear model is the grading of two aliens. And we already saw that there is a link between the representation of these aliens and the OP, the fusion rules of primary fields in conformal field theory, and essentially the conformal dimensions of the primary fields provide you information about the monotony, so what happens when you move one alien fully around one other. So by knowing the conformal weight of the primary fields, you know the square value of the braiding methods. And in particular, the braiding is such a way that if I have A and B in my braid them, I never change their total charge C. This is because the braiding is something that affects the inner structure of a system. So if I change the position of this two, I am applying something that from far away I do not really distinguish. And so if the total charge of this system is C, it must be C before and after the braiding process. That's why if I consider a given basis, so the integral space that I was writing before, V, A, B, C, in this integral space, the braiding matrix between A and B must be diagonal and must assume these values that, as I told you, once you square them, they must correspond to this in terms of the conformal weight of the underlying. However, it is not enough to have a representation in this diagonal basis if we want to represent different braid generators of different particles. And as I told you, the main characteristic of the non-abelian aliens is that two processes which I exchange A and B, so something like that, and C work in this way, in which I change B and C without touching A. Of course, these two objects do not commute. But unfortunately, if I choose a basis, R of A and B will be diagonal, whereas this new exchange will not be diagonal in this basis. So I have to use these F matrices to represent all the generators of the braid group in a common basis, essentially. I guess that we can stop here for 5 minutes, and then we will see how these things are realized for Fibonacci and easily. Yes.
So you have yes, apart from
Yeah.